We are recording. Great. So good morning and thank you for joining us. The purpose of today's session is to give you information about a research experiences for teachers across the National Nanotechnology Coordinated Infrastructure. My name is Dr. Quinn Spadola and I'm out of Georgia Tech in Atlanta. And we have a few things we're going to cover today for all of you. This is not a webinar. I set this up like a regular Zoom meeting. So if you have questions, feel free to either chat or unmute yourself. And we'll probably take questions after each of these sections and then also at the end. First, I'm going to give an overview of the Research Experiences for Teachers program. And then Steve from Nebraska is going to talk about both what nanotechnology is and, as a former RET himself, a little bit about how this has impacted his career. Jim from Minnesota is going to talk about careers in nanotechnology, so everyone has an idea of how useful having this knowledge is for your students. Elizabeth from Northwestern is going to take us through a remote scanning electron microscope session. And then we also have faculty from the various sites, just a few, actually one from each site or so. They're going to give a brief overview of the type of research project that you could expect to do at the various sites this summer. And then last, Leslie, also from Georgia Tech, is going to do the drawing for the STEAM kits that we said we had a raffle for at the end. All right. So to begin with, here's a map of the National Nanotechnology Coordinated Infrastructure, which is an NSF-funded network of academic nanofabrication and characterization sites across the United States and their partners. This Research Experiences for Teachers program involves 4 NNCI sites, the ones that I just put boxes around. And the purpose of networking these 4 sites is so that all of the educators who participate will be able to get to know a larger group of their peers and be exposed to more areas of nanotechnology research, and also learn more about the different career opportunities that are across the United States instead of just locally, although you will learn locally as well. The purpose of the Research Experiences for Teachers program is to support both high school teachers and community or technical college faculty in authentic summer research in these academic labs with faculty and either graduate or postdoc mentors. The research projects and experiences all revolve around nanoscale science and engineering. And then as part of the experience, each of you, the ones that are accepted, will translate what they've learned about nanotechnology into classroom activities and curricula that you can then take back for your own students. This is information about the RET itself. The whole program lasts 7 weeks, 6 weeks of which are going to be during the summer. And as you can see, each of the 4 sites, the dates are a little bit different to accommodate the different schedules of the local schools. And there's a representative from each of these sites on this call. So if you have questions about specific sites, we'll be able to take those as well. And then 1 week during the school year, and that's 2 parts. One is that either one of the RET staff or perhaps your mentor that you've worked in the lab, someone will come out to your classroom and help you with implementing the curriculum that you will develop over the summer. So we'll join you in the classroom as you do this part. And then lastly, you will be expected to go to the National Science Teachers Association meeting in the spring to talk about your experience. We will submit a workshop proposal, so hopefully you'll be able to present on the curricula that you developed in the summer. And this is completely covered by the program. This is a free trip to the NSTA in the spring. That is covered if you were an RET. So what the RET provides to educators. There is a stipend. It is paid out in increments. The travel to the NSTA is also covered, as well as funds to support the development of that curriculum so that you can purchase classroom materials to bring into your classroom to implement whatever you develop. There will also be hands-on research experiences in nanotechnology, doable research projects for that 6 weeks in the summer, and you'll have the full support of the faculty and the mentors in the lab. As it says here, faculty research advisors and graduate student mentors. You also have the full support of the RET staff. And then what you can expect. When you start the RET, the first week or so, you'll go through the environmental health and safety training and any training related to your research project for the lab training, clean room orientation if you're going to be in the facilities, and training on any necessary tools. You'll be placed in your lab and you'll have a mentor, a graduate student or a postdoc who you'll be working with day to day. And then you'll also be meeting with your faculty member whose lab you're working in. Because this is a networked experience, in addition to your research experience, you're also going to be meeting regularly with all 4 sites. So all the teachers across the NNCI RET will be doing this virtually. And many of these activities will be providing you with reading materials on nanotechnology, lesson templates, examples of previous activities that have been developed, time to allow you to brainstorm and develop your classroom curriculum. We're also going to be connecting you to what we're calling pen pals. These are educators from the other sites that you may have something in common with, either the research project you're doing or perhaps the curriculum you're considering developing or the subject matter you teach at your school. But we're going to make sure you get connected with your fellow teachers. We're also going to be having industry speakers come so you can learn more about the types of companies and jobs out there. And throughout the summer, you're also going to be presenting on both your research and the classroom activities that you develop. The research presentations are so that all of the teachers across the RET get an idea of the types of nanotechnology projects that are happening. And then the presenting on classroom activities is so that you can receive feedback from your fellow teachers. And this is what we are expecting from you. You are to complete the full 6 weeks of the research experience in the summer. And this is a full-time job. We're expecting 40 hours a week for those 6 weeks. You'll attend all of the summer meetings and seminars that we'll be planning for you, that you will develop the instructional unit based on the experience you're having, and that you'll welcome someone from the NNCI into your classroom to help implement the first time you do that. We also expect you to attend and participate in the National Science Teachers Association meeting. And as I said, that is a free trip for you. Your travel is all covered for that. And then lastly, we'll ask that you provide a webinar on what you've developed to the Teaching Nano and Emerging Technologies Network. Eligibility to apply to the RET, you must be a high school teacher, 9 through 12, or a community or technical college faculty. Teach a science or technology, and you have to live within commuting distance to each site. This is a non-residential program, so if you live in the Atlanta area, Georgia Tech will be your site. You can ask and request to go to one of the other sites. It is residential to the site local to you. We do not provide housing. And I think this is my last slide on the introduction to the RET program. Here is the website where you'll find out more, and then the contact information for each of the program coordinators at each of the 4 sites. I'll be posting this presentation and all the rest of them on this website after today so that you can get in touch with everyone. And are there any questions? And feel free to either unmute yourself or use the chat if you have any questions. All right. Excellent. And if you think of anything throughout the rest of this, just go ahead and ask. Oh, I do see something popped up in the chat. Oh, yes, I can go back to the last slide. You mean the one with the contact information? Well, so that's an excellent question. How flexible is the program to fit around family vacations, etc.? This is 6 weeks that we are scheduling this. During these 6 weeks is when we'll be providing all of the virtual interactions with the other sites. These are the 6 weeks your mentor and your faculty people are expecting you to be in the labs. So we're asking that you not take any sort of extended family vacation. I'm not going to say you can't take a Friday if you've cleared it with your mentor and you're prepared to watch anything that's been recorded. It's not that strict, but do not request to take a full week off partway through the 6 weeks. So there isn't that much flexibility. And you're looking at a 40-hour week. You can make it flexible with your lab. We are going to schedule all of the virtual meetings within standard working hours. We know that there is a time zone difference. So I promise you that people in the central time zone, we're not talking 8 o'clock in the morning. We'll make sure it's 9 or after and before 4 o'clock. We'll schedule those meetings, but we are expecting a full time, 40 hours a week. No, if you're, this is just an interest meeting. There is an application link, which I'm going to put in the chat as soon as I'm done reading all of your questions. And the application link is also on this website as well. So there is an application that you'll have to fill in if you're interested in participating after our virtual session today. Okay, so what are the COVID-19 protocols for the lab space at Georgia Tech? I was completely expecting this question. As of right now, we are all planning to have you face-to-face working in your labs, and all of the labs that have submitted projects, for example, to Georgia Tech, understand that they will be following the density limitations that are in place. We said plan for what's happening in the spring in case it extends to the summer. So then you will be required to wear a mask. At Georgia Tech, and the other sites can speak to this, you will be hired on as an affiliate. So you will have access to, so you will be considered a Georgia Tech employee. So you will have access to the surveillance testing that they are currently doing right now on campus. So mask, participating in the surveillance testing, the limited density in the lab. So you'll work that out with your mentor and your faculty member. I know that many of the labs have schedules, but they also know to expect that. So there are protocols in place that you will be expected to follow, but I think masking, the low density. In addition, if we meet with you in person for any of these virtual activities, we are already securing actually rather large seminar rooms for just the 7 of us so that we can do the social distancing if we're in person as well. Yes. I'm going to share the link on the screen as soon as I am done because I have to unshare my screen, although I guess I could do that now. You mentioned presenting research at the NSTA conference. Can you talk more about that? Certainly. Oh, thank you, Katie. So the NNCI will have a booth at the NSTA conference. And so that is something that we attend each year. And so you will be asked to spend some time at the booth talking to teachers. In addition to that, I'll be submitting a workshop proposal to the NSTA. And if that is accepted, then when you're at the NSTA, you'll also be expected to participate in that workshop where you'll also present what you have learned. So those are the 2 activities we'll expect you to participate in. Could we present at NATS? What is it? I don't even know what NATS is. Could whoever, Sandra, what is NAT? What conference is that? I'm mostly familiar with NSTA. Oh, is that Nebraska's Science Teacher Association? You are absolutely, we will be encouraging you to present at your local conferences. Absolutely, that is something we would love to see you do. And so if you want to present at your local state Science Teachers Association meetings, absolutely. We encourage you to do that, but you will also be expected to go to the NSTA. All right, great questions, everyone. Thank you. And if any more come up, we will be certain to answer those. Well, and so Kimberly just asked, do we have examples of the topics? We are going to, when we get to that point, we're going to give you a couple of examples of the types of projects that we'll have available for you this summer. That's going to come after Steve and Jim and Elizabeth do the SEM, but we will give you examples. And they're also, depending on your site, Georgia Tech, for example, our project descriptions are up on our RET site. And with that, I'm going to turn it over to Steve. Thank you.
Okay. Good morning. Can you hear me? Great. Okay. I'm going to be presenting to you about what an RET is, what nanotechnology is all about. I was an RET at the University of Nebraska for 15 summers. And from that, I ended up getting to work at the position I am right now part-time. I'm part of the NCMN and the NNCI and NNF and all these other organizations. When I write my name out, it just gets longer and longer with all of the things after it. But so what I'm going to do is I'm going to share my screen, and I'm going to make sure I share sound. Okay, can everybody see the PowerPoint? Good. We'll go ahead and open that up. All right, so this is about the summer RET and a little bit of intro into the nanotechnology. We'll start with that. So our objectives today is, what is nanotechnology? How can I integrate it into my teaching? And how could I grow as a teacher through this experience? Okay, some simple definitions for nanotechnology is the study of manipulation of matter on the atomic scale. Refers to the constructing and engineering of the functional systems at a very micro level, or we can say at an atomic level. And when we're talking about a nanometer, it's 1/1000th of a meter. So it's roughly the width of 3 or 4 atoms. A human hair is about 25,000 nanometers wide. Okay. So where did this come from? Okay. Richard Feynman kind of started the concept of what nanotechnology is, and then it was later coined in about 1981 by Professor, I'm going to mispronounce this, Norio Tamaguchi. And, basically it's a newer science. It hasn't been around that long. And if you want to read more about this, we'll have slides available, these PowerPoints, so you can look at these more later. So I don't want to take all the time up today. This is a short video. This is through NBC and the NSF. And it's about 4 minutes long, and it does a really good job of introducing nanotechnology and how it covers all the different sciences and fields. So I'll go ahead and share this.
Colorful butterfly wings, strong and sticky spider silk, water-repellent leaves. Some of the most fascinating things we see in nature are possible because of things we can't see. Materials, structures, and architectures on a scale so small they're invisible to the naked eye. For scientists and engineers, the nano, or billionth scale, is a vast new frontier where the ability to manipulate and control materials smaller than a fraction of a hair offers amazing opportunities for new materials, devices, methods, and applications. Called nanotechnology, it's already having a big impact in a lot of areas like medicine, electronics, nanostructured chemicals, energy, and optics.
You have nanotechnology in your everyday life right now, and you may not be aware of that.
At the University of Pennsylvania's Singh Center for Nanotechnology, Dawn Bonnell is a materials science and nanotechnology researcher and is funded by the National Science Foundation. She researches nanomaterials, including oxides, carbon, and gold, which could be used to develop new devices. She also invents new scanning probe methods to measure material properties at that small scale.
We work in the range of 1/10 of a nanometer up to several hundred nanometers.
Exactly how small is a nanometer? Consider that 1 billion nanometers equals 1 meter. The head of a pin is about 2 millimeters in diameter, the equivalent of 2 million nanometers. The width of a human hair, about 100,000 nanometers. The diameter of a strand of human DNA, 2.5 nanometers. Lined up, 10 hydrogen atoms measure 1 nanometer. At this incredibly small scale, Bonnell and her research team are studying the surfaces of a variety of materials to better understand how atoms on those surfaces behave. Knowing how nanoscale materials behave can give scientists and engineers the ability to manipulate them.
The first part of trying to control and harness nanoscale properties is to understand them.
Scientists have found that the properties of nano-sized objects behave very differently than at larger scales. For example, a tiny piece of gold, only 3 nanometers in size, will look more red in color and have a lower melting point.
We do a wide range of experiments on those atoms to try to understand how they behave, and that helps us to think about how we could build devices out of them, how we could do useful things with them.
Scientists and engineers often work in controlled environments, labs that are free of dust and other microscopic contaminants that could interfere with research and fabrication.
Clean rooms are an environment where there have been filters put in place and insulation from sound and insulation from vibration that allows the environment to be pristine.
Bonnell and her team use special instruments that allow them to see at the nanoscale. Scanning tunneling and atomic force microscopes make images of a material's surface by using very sharp tips that interact with the surface. Using these tools, they can make very fine, detailed images of atoms on the surface of materials, allowing scientists to examine the properties of atoms.
And that is one of the excitements about scanning tunneling microscopy. It was the first time that we were able to image atoms, and that revolutionized how we thought about making nanoscale devices, that we actually could make them, even 1 atom at a time.
Bonnell explains that the ability to see and manipulate materials at the nanoscale was a huge step for nanotechnology.
It opened up our eyes to the possibility of using those properties that are special at that scale in a way that we wouldn't have been able to think about doing it before.
Scientists are already exploiting the special properties of nanomaterials with nanotechnology in products like stain-resistant clothing, cosmetics, and sunscreens, and electronics like smartphones, televisions, and computers. Nanotechnology could help with more efficient manufacturing, diagnosing and treating disease, cleaning up the environment, energy solutions, even protecting firefighters and soldiers.
There are tremendous opportunities because we're able to do things at such a small scale with such precise control. I think we're just at the very beginnings of being able to harness those properties that we're measuring.
For Bonnell and her team, the nanoscale is an opportunity to solve problems and improve quality of life, where great possibilities begin with something very, very small.
Okay, so let's talk a little bit more about nano and some size comparisons here. We have our macro scale, which we're used to because that's our lives. And then we have a micro scale, which you have like the diameter of hairs, E. coli, bacteria. And then we have the nanoscale, which you'll be working with this summer if you decide to go into the RET. And in the video, it showed some ways that we can see what we're working with, because these things we create or research are so small that we have to have other ways of seeing those. Later in the presentation today, you'll learn about different applications. This is just a general diagram showing some different ways that nanotechnology is used in research and our everyday lives. It's getting to be more and more that way. And as I taught high school physics, science for 37 years, and I know as a teacher in the public schools that, you know, it's important that we have the curriculum integration into our standards. You know, the standards have changed tremendously over the years, but now we're into the next generation science standards. And this is just a list of some of the ways that if your administration asks you, how can I integrate this into my teaching? These would be ways that it would fit into the curriculum. And as you notice, some of these are very broad. The first one, the HSPS26, is probably the most general and the one that will tie in the most with about anything as far as the nanotechnology. And then there's some other ones listed under there that, you know, are maybe elementary or middle school. Well, middle school down at the bottom, but there's a lot of ways that you can work nanotechnology into your lessons and have it be acceptable and be part of the next generation science standards. As far as curriculum, we have a site through the NNCI where, you know, there's already a lot of resources for educators. If you go to that site, you'll see lots and lots of ways that nanotechnology can be integrated and used in your curriculum. When I was in RET, a couple of the first projects that I did as far as developing curriculum for my classroom, I did a unit on organic solar cells with Professor Ducharme, who's going to be speaking later today about how he's going to work with you in his lab if you're part of the Nebraska NNCI. And then also he had a lesson that he'd been doing in some of his labs on LEDs and Planck's constant. So we took that and we worked it into a PowerPoint presentation so that it could be used by other teachers in the state. So, you know, this tied in with the type of research we were doing at that time. And over the 15 years, I did quite a few different projects with the lab and different research. Okay, so if you would go to the website for the MERSEC, which was the RET that I was involved with, this was a description of one of the summers when I was working there of what I was doing as far as my research. I was working with dip salts and we were trying to find ways to reproduce it consistently and have a good substance that we were producing. And also as part of that, over the summers, I got involved with different types of outreach. We were part of like Upward Bound. We were part of Bright Lights. We had a camp on nanotechnology that we did. I worked with pre-service teachers. You know, this was really gratifying to me because I got to share with some of my future peers. I got to teach about nanotechnology to all kinds of different groups, and it was just, you know, great. And that's kind of what I do now as an outreach one of the outreach coordinators at the university in the physics and in the nano, the NMF, is, you know, I set up these things, and we're doing a lot of virtual right now, but we're still doing a lot of teaching. And this is something that maybe if you get involved, you can get into this more. And this was a great experience for me. Also during those years as a RET, I got to go to conferences. This picture here was the first one I went to. This was in Boston it was part of the MERS, and we did a poster presentation of the research I was doing in the lab at that time. And also we presented a paper on research experience for teachers and material science, a case study. And I did that with the professor I was working with at that time. And it was just great. I mean, going to that meeting, talking to other educators and people in nano with the research was wonderful. And then, it opens other doors. I mean, depending on how involved your site is, you find different ways. I mean, with the solar and the thin film type stuff we were doing in Professor Ducharme's class, one of the other RET teachers and one of the grad or postdoc students that was in that lab, we got the opportunity to go and see one of the first Teslas that was going cross country. It was going through Lincoln at the time and was fueling up at the wind turbine on the edge of town. And, we tied that into some of our, our teaching experiences and learning experiences at that time. Okay, so just, finishing here, I'd like to say this has been, one of the greatest experiences I've ever had as far as getting involved and keeping, education alive with me. You always want to learn and you want to share that. And what you can take back to your students is just immense from this project. I mean, you can make out of it what you want. And so with that, I'll open it up for questions, and thank you for taking your time today. Saturdays are tough, but I think this is important. So thank you. So
I have a quick question, if you don't mind.
I guess.
Sure. As a teacher and being out of college for a few years now, it seems a little intimidating doing like genuine research at the university level with a professor. Do you feel like it's pretty approachable, or could you talk about that a little bit?
I was scared to death the first year I went in, because I went into a lab, and what we did in that lab was we were making iron nanoparticles for medical purposes. And I worked with one of the grad students. Well, he was a postdoc, and he was so super friendly and approachable. And he first day, he just kind of went through what we were doing, and they really work you into what you're comfortable with. I mean, they're not going to try and say, okay, here's what you're going to do and good luck. They're going to be very good with you as far as helping you along. I mean, I was, this was, I got a pamphlet in the mail from the university saying, we'd like to have people come down and do nanotechnology with us. And it was new for them too. It was only in their second year of the program. And it just, I went in there thinking, what have I gotten myself into? And I understand where you're coming from, but look, 15 years later, and those 15 years went really quickly. And it was every year it was like, what are we going to learn this summer? And, they'll take the time, they'll teach you, they'll make sure that you understand. So don't feel intimidated, when with a very optimistic viewpoint, and because it's good for you. So.
Excellent. Thank you.
Yep. Okay. I'm seeing a lot of things in the chat. Do you want me to go ahead and try and answer a couple of those, Quinn?
Sure, please, Steve.
If you can, I'm getting quite a few. Let's see. Could you share your experience of doing research? Oh, that's for you at the Georgia Tech Lab. Is there any expectations in terms of how to use the equipment? No, you're going to be trained on equipment. You have to go through the same kind of training as all the undergrads and anybody coming in from commercial use or whatever. You're not going to just be, okay, here's the electron microscope, go for it. You know, this equipment's expensive. They do not want you to just jump right on it and try and learn it on your own. So no, there's no expectations. You'll be taught what you need. So, and I don't know, did you want to answer that other question? I kind of went.
So, to be quite honest with all of you, I have never gone through an RET at Georgia Tech. I am helping to run the program, but if someone, for example, Nancy, it's funny, she put the, oh, Fred, could you share your experience of doing research at the GT lab? So Nancy Healy, who is from Georgia Tech, invited one of the teachers who's online if they want to talk briefly about Georgia Tech.
Yes, like
The
previous speaker, Steve said, there is no expectation that you had any prior knowledge. When I was there, I spent the first week reading up on nanotechnology and eventually decided on an area and topic to work on. Once you decide on what you're going to work on, you are trained and you participate in weekly workshop so that you get familiar with the people working in that area and the equipment, including the clean room that you'll be working with. And every time I use the equipment, at least the first 2 weeks, there was somebody there to direct me until I was comfortable to use some equipment by myself. Again, like Steve said, there are other equipment that I was not allowed to use by myself throughout the period of the program. And in terms of other experiences, we had a weekly meeting with Nancy where we gave update of our progress. And then at the end of the program, we did a general presentation. Then later on in the semester, for that one day that we had to come back to campus, all participants from the different centers came together a couple of days and we gave presentation on our topic to the general group. And of course, we got our money, we got our stipend into installment. And later on, we actually, before we left, we put in requisition to get supplies that we took back to our schools. That's how my experience was.
Thank you for sharing.
Okay, thanks.
There was a question about, is the RET a one summer thing? This program, Steve is a superstar because he kept doing an RET every summer. The program that we are talking about right now is funded for 3 years through the NSF. Maybe it'll extend past that. That's the length of this program. I will say, however, that each of these NNCI sites and the people that you're meeting today from them, part of our jobs and part of our passions is to provide resources and support for teachers and educators. So even beyond the RET, there are a lot of resources for NNCI, from NNCI centers. And that's something not for today, because I don't want us to go longer than we are scheduled to. But if you email the people from your local sites, we can give you more information about that. But this RET right now is to last for 3 summers. And the expectation, if you apply, is for this coming summer. Georgia Tech, each site will be 5 teachers. So 5 teachers at each of the sites. How many teachers per year do you recruit? And then there was a question about publishing. Steve, do you want to take that? Because I think that speaks to, you can make of this experience what you want.
The publishing was done with Deandra Pilecki, who was my professor at that time with the first research I did. And basically there were 3 RETs that summer, and what she did is she worked with us and gathered our information for that paper, and then she's the one that put it all together and then presented it to the MERS conference, where it was judged, and, and then we actually got an award for that. But, if you do any kind of publishing, you're going to be working through your mentor or your professor that you're working with anyway. So, it's not something you have to do. It was just something that they thought was a good idea, and, it worked out real well. So you get your name on a published document. So it always looks good,
Steve and Quinn, if I could also add something, it's not just your laboratory research that it can be potentially publishable, but also the curriculum you developed. One of the papers we had that came out of a chemistry group ended up in the Journal of Chemical Education. So that's another option.
Right.
And with that, Jim, do you want to move on? Thank you very much, Steve.
Yep.
And thank you everyone for your questions. Jim, do you want to move on?
Yes, indeed. Let me pull up what I'd like to show folks. Okay. That's not what I wanted. All right, so everybody see that screen? Is it in presentation mode or not? Should be.
It looks good. It looks
All
good.
right, good. All right, very good. Good morning. I'm Jim Marty. Thanks a lot for joining us here this morning. I'm from the University of Minnesota. And I'd like to spend the next few minutes covering answers to a question that your students may raise. Is, I'm excited about nanotechnology, but can I get a job in it? Are there careers to be had here? And yes, the short answer is yes. And I think that the longer answer is there's just lots of different paths to working in nanoscience and nanoengineering and applying what they may learn in a nanoscience program. Kind of laying out the terrain, there's nanotechnology is found in a lot of different applications, and so there's a lot of different job titles associated with it. You may work as an engineer, or your students may work as an engineer. Here you're developing the devices and materials that operate with some key parameter that's important at the nanoscale. So electronics and material sciences are areas that nanoengineers may work in. Farther upstream in the development chain, you have the nanoscientists working with more fundamental studies of new materials such as graphene that present real promising potential for new devices and materials and products. But at this point, they are working with more basic science. There's a large number of people who use nanotechnology knowledge in a technician or a technologist role. At many, many companies, there's laboratories that employ technicians that are doing routine analysis, material testing, quality control, and so forth. So the fair number of people that don't have nanotechnology in their job title but are doing that as a technician or a technologist. And then probably the largest group.
See, wherever you push, it's going to move.
Is there a question? Okay. Maybe the largest group involved using nanotechnology are people that are using some nanotechnology as an end user, maybe in manufacturing or in environmental monitoring or the like. There, it's helpful to understand more about what's happening at the nanoscale, simply so you can be more confident in what you're measuring, what you're testing, what you're carrying out. So all of these are called, could be called nanotechnology careers. The trouble when students maybe go out and do a little searching on their own for jobs is that they aren't always called nanotechnology. So when, in answer to the question, are there jobs out there in nanotechnology, you're going to get a variety of answers. One thing we do know on this, the top statistics there, science, technology, engineering, mathematics jobs, STEM jobs, did increase about 20% over the first decade and a half of the 21st century. The National Science Foundation has always said that there are going to be large numbers of new nanotechnology jobs needed. A 2010 estimate was about 2 million by the year 2020. That number is accurate depending on how you, again, define nanotechnology jobs. On the other hand, if you do like I do, I went to careerexplorer.com website to see what some other numbers are out there. This was a relatively modest number of nanotechnology engineers quoted, and a relatively modest job growth in that market, about 6.5% over the next 10 years. Now, that's low simply because nanotechnology jobs encompass a much wider variety of tasks and skill sets than just, quote, nanotechnology engineers. So to really look at possibilities for your students in nanotech, you have to kind of look at a huge range of job titles. This is a partial list of the job titles that I had some of my students look for when we were looking. I was involved in a 2-year technical training program in nanoscience and technology. And looking for a nanotechnician is not going to reveal too many hits. But all of the job titles listed on this page employ some aspect of knowledge of nanoscale phenomena and nanotechnology applications. And so these are all areas in which we were able, my students were able to find leads, and we actually placed a number of students in jobs with similar titles to this. So that's what the job titles might be. Where would they work? What kind of companies, what kind of environments would nanotechnology, students who go into nanotechnology do? So a big employer of nanotechnology savvy workers is the electronics industry, the integrated circuit manufacturing, the big players like Intel, AMD, Qualcomm, Hewlett-Packard, as well as a number of smaller players doing the task of fabricating integrated circuits and integrated circuit-based devices. And this is a task which would lead the worker into a clean room environment using the tools of lithography to fabricate millions or billions of small transistor-based circuits on a chip of silicon to form an integrated circuit. This is a very cyclical industry. It goes up and down, as you may know if you have people who have friends who work in the area. But right now, this industry really needs people. There is a shortage of integrated circuit chips, you may have heard, in this country, which is affecting downstream manufacturers in the automotive industry and electronics and so forth. And that is part of it is personnel related. I've had a number of companies local to the Twin Cities contact me and see if I know of anybody who can step into the clean room role and do some lithography. So this is a hot area right now. Perhaps a bigger sphere of industry that uses nanoscience is the specialty materials companies, those that make particles, nanoparticles, or nanostructured materials that end up in a wide variety of consumer and industrial products: paints, pigments, coatings, filters for water and lubrication oils, sealants, security inks for currency, displays, and the many different types of particles that go into personal care and cosmetic products. These are all companies that are consistently hiring. And again, knowledge of the nano scale, especially the chemical aspects of nanoparticles, this is a very good place to find employment. An exciting emerging area of applied nanoscience is in the area of drug delivery. So pharmaceutical companies like Pfizer and Abbott and GlaxoSmithKline are all working in these areas of encapsulating drugs so that they are better at getting where you want them to go. On the right-hand side of the screen, there's a couple of different types of encapsulation approaches using lipid molecules, the bifunctional molecules that have a hydrophobic end on one end and a hydrophilic end on the other end. And these can be fabricated into little cells or little capsules that can very effectively deliver either hydrophobic or hydrophilic drugs to the patient. Even more advanced area is taking nanoparticles, like is pictured on the left-hand side, and attaching molecules to the surface, which can, if you attach the drug molecule on it, you can deliver the drug molecule with that particle, and B, you can attach a little bit of a targeting molecule, such as a protein or an amino acid, which will help the particles stick to the tissue you want them delivered to. So this part of nanoparticle drug targeting has resulted in a couple of FDA-approved therapies for cancer medication, but it opens up a lot of possibilities for direct dosing and much more efficient treatment of many diseases. So nanoparticle drug delivery, a very exciting area for pharmaceuticals. And in particular, right now, you may know that the COVID vaccine is based on, not on a weakened whole vaccine, but on a piece of messenger RNA. Well, you can't just squirt that into a patient. It has to be encapsulated in a lipid nanoparticle. And then, as you can see in the cartoon on the right-hand side, that nanoparticle is able to be absorbed through the cell wall, and then get into the cell nucleus so that it can operate. This is a very promising technology because it promises to be the way that we develop future vaccines. It enables us to go much faster in the development process. And there's a shortage of, I mean, this is one of the shortfalls in rolling out the COVID vaccine, not the only one, of course, but in terms of getting the designing and maintaining the equipment to make these lipid nanoparticles and having a knowledgeable operator, this is definitely going to be a growth area for those that know about nanotechnology. There's also more prosaic applications of nanotechnology, nanoscience, or particle science, particularly in the food processing area, where big food companies are routinely developing new products based on particles or powders that have to have certain properties and formulations to add color, flavor, texture, other properties to the food product. So again, knowing about microscale and nanoscale phenomenon, particularly as it regards to fluids and droplet formation and so forth, a big employer of people knowledgeable about this area. And there's a large kind of invisible market sphere of analytical labs. These are mostly small to medium-sized companies, but they employ technologists and scientists who are going to be exploring the physical and chemical and in some cases biological properties of samples. And knowing the technology, knowing the analytical technology, like you would learn in a nanoscience program, this is a place where you can apply these skills as well. So lots of jobs in lots of different areas. And a range of working environments as well. When I was working with our local two-year nanoscience program, I had placed a lot of our students in small companies and in startup companies where a lot of exciting work is done and offers the students a real opportunity to grow, because at small companies, you tend to have to wear lots of different hats. You may learn about engineering as well as business development or sales or the other people parts of the business. So much should be said about small companies. On the other hand, large companies are also hiring these folks and can offer advantages, such as offering to support further education. A number of my 2-year associate's degree students join companies which then sponsor their completion of a bachelor's degree, and in some cases they're going on to an advanced degree. So a lot of different environments, a lot of different job titles, a lot of different things to do for students who are interested in this area. So I want to encourage you, if you have students that are interested in this area, offer them the unvarnished truth that, yeah, there's lots of jobs out there. In terms of preparation, you can advise your students, yeah, you're going to want to concentrate on high school subjects of chemistry, physics, and biology. These are all good preparations for nanoscience, nanotechnology careers. Options after high school are at all levels. Those who are interested in 2-year college programs, associate's degrees, there are several programs around the country that offer 2-year associate's programs. And a good clearinghouse for that information is a new education center and National Science Foundation funded center called the Micro Nanotechnology Education Center, or NNTEC, that has information about these programs around the country. Those students who are interested in a bachelor's degree, there's relatively few 4-year programs called nanotechnology programs. I mean, getting a 4-year bachelor's in nanotechnology is fairly rare. More common is that students will pursue traditional engineering discipline degrees, such as electrical, mechanical engineering, biomedical engineering. Even civil and environmental engineering is a pathway into a nanoscience career. At the higher levels, the more advanced degrees, typically people are working in the physical sciences or biological sciences in some cases pharmaceutics, and also the advanced engineering is also a pathway to be out on the nanoscience end of the program. So just to wrap up, a couple of websites to look over. The nano.gov website has a great introduction to nanotechnology. You may also want to check out that 2-year nanotechnology training program clearinghouse, Micro Nano and Mintech. That is getting a new website. So they have kind of a temporary space holder website at this address, but there's going to be a new more elaborate, more useful website launched soon in that area. We can share that with you when it comes available. And then I'll point you to our own NNCI website for a nice overview of other careers in nanotechnology. So with that, I will turn it back over to Quinn. I'd be happy to answer any questions.
Thank you, Jim. I saw one question pop up while you were speaking, and it was about opportunities to work at the intersection of medicine and nanotechnology at the University of Minnesota. Are there projects and opportunities for teachers?
There are, and in the past we've had RET teachers work with the biomedical engineering department on a biomedical device that was an advanced form of ultrasound detection, ultrasonic detection. So developing better probes and algorithms to improve ultrasound analyses. That's one example of an intersection. We also have the Institute for Engineering and Medicine at the university, and other universities have similar places where there's a lot of interest in exploring that intersection between medicine, the life sciences, and nanotechnology.
Great. I haven't seen anything else pop up. Nancy put some more resources in the chat, and I think we'll move on to Elizabeth at Northwestern to do the remote SEM and give you guys an idea of one of the instruments you will most likely be using.
Hi everyone, I hope everyone can hear me. I'm currently sitting in one of our lab spaces at the Northwestern Atomic and Nanoscale Characterization Experimental Center, where you will be able to work and use all of our different instrumentation. This is just one of the centers that you'll have access to during the RET program at our university. And it's a user-based facility where faculty and grad students and external companies come in and use our equipment on a crazy amount of different applications. We have people from the art museums, we have energy companies and medicine and materials and environmental remediation and all sorts of things like that. So there's really no shortage of different topics that people look at here, and depending on your interest, we can match you up with someone who has similar interests and kind of customize a project for you. So I'm going to share my screen and you'll be able to see what I have been working on this morning. Okay, can everyone see that?
Looks good.
Cool. So I won't be able to look at the chat. So if Katie will let me know if there's any questions, or Quinn, but I will be happy to answer any questions at any point. Go ahead and interrupt me. I thought we could start off here if anyone wants to guess what I'm looking at in this image.
Atom.
Sorry?
An atom.
No, so this is actually a camera lens from a smartphone. And you can see down here, this white bar is our scale bar. That's what 1 micron would be in this image. We're at an 18,000 times magnification. So these are very small photo sites, they call them, and they each individually receive photons and light from the surroundings and turn it into a electrical signal that your camera can then use to put together an image. So this is definitely getting down to the nanoscale environment, and it's huge in electronics and optical cameras and other microscopes and other things like that. But I wanted to compare this to another sample I've got in here.
Elizabeth, do you want to tell them a little bit about the instrument you're actually using right now?
Yeah, so this is the JOL 7900 scanning electron microscope. It's our newest one, and it is it has just incredibly good resolution and lots of really great toys to play with. and look and characterize your sample in many different ways. So I wanted to compare that camera to the structure on this. This is actually the eye of a bug that I found in the office this morning, actually. And you can see that it's not, obviously it's not identical, but it's a very similar structure down at these higher magnifications. And it works in a similar way where it's able to look, receive more 2D information from many different angles and kind of stitch it together into a 3D image that the fly can then see. But you can also see with a scale bar, this is actually much bigger than the optical microscope. So we've kind of improved upon the design for our cell phones and cameras that we use in our day-to-day life. So those are two, kind of vastly different specialties. We've got biology and then we've got materials and physics on one side, but they can be very closely related. And no matter which discipline you teach, you'll be able to use these tools to incorporate some images and analysis from here into the lesson. So there's that bug's eye. Bugs get very gross and very interesting at these high magnifications. So students always seem to love that. Let me go back to so this is a penny. This is actually the back of a penny. You can see that this is kind of a live optical view. And then this is my electron image, which is produced by the electrons interacting with the surface of my sample. And so you can see on the back of the penny in the Lincoln Memorial, we have a little tiny Lincoln sitting right where his statue would be. And if he had eyelashes, the size of his eyelashes would be 1 nanometer each. So that's another kind of scale to give you for the kind of things we can look at with this instrumentation. So this is a method that is used in, I know the video earlier mentioned scanning tunneling microscopy and atomic force microscopy, and those actually physically will touch your sample. This is just an electron beam, so it's a little more sensitive to maybe more biological or physically sensitive materials. So there's our little Lincoln. He's on all the pennies. You can also, with this kind of equipment, you can use energy dispersive spectroscopy, which uses the same signal that we are using to make this image to analyze what the material is that we're looking at. And you'll be able to see with that kind of thing that after 1982, they went from copper pennies to zinc pennies plated with copper. So they look the same, but internally they are zinc instead of copper. And you would be able to tell that with this kind of instrumentation. You'd be able to choose an area of interest and it would tell you exactly what it was made of. And you could do that simultaneously as you image things. So it's really a great one-stop shop for trying to get to know what kind of sample you're working with. And another thing I heard mentioned in the videos before was the butterfly wing. So those morpho butterflies, the really like strikingly blue butterflies, don't necessarily have pigment in their wings. It's actually a structural shape that allows the blue wavelength to be refracted and reflected out, and gives it that brilliant blue color. So when you get down to these really high resolution magnification and high resolution and high magnification images, you can start to see the structure that results in that color.
So we're zooming back out now, right, Elizabeth?
Yep, I'm zooming a little bit back out. This kind of instrumentation is so versatile. It's very versatile in what kind of scale you're looking at. It is very useful for nanoscale, and it's also very useful for, this is only 170x magnification. So it's great for both. It's kind of something you can easily and quickly, zoom in and out and get different images without having to go through. With optical microscopes, while they might be simpler to set up, they have a limitation of roughly 1000x magnification, which we are not limited by. And you also have to, change the objective and all that kind of mechanical change. So this is a little bit more software based, and so you can use this in many different ways instead of having to drastically change the instrument every time you want to look at something different. Yep. So does anyone have any questions on the samples that I've been pulling up? I've got one more. Another thing that we've seen quite a few users come in with, oops, that's the wrong one, are microfossils. And they can be, millions of years old. And I believe these are 3 million years old, the ones I'm looking at right now. And they are found absolutely everywhere, in puddles, in sand, in dirt, they're just everywhere. And they can give us a lot of information on environmental conditions and geology and things like that. I'm not a geologist. I know we have one in the chat, so if you have any questions geology-wise, I would point you to her. But they are
Elizabeth, someone asked about the images. Can they be colorized or only in black and white?
So the way that the software, the signal it receives from the sample electron beam interaction is turned into a grayscale value. But I know there's a lot of post-processing software that people use to color things if they know what color they want them to be for their paper. But in general, the electron microscopes will give you black and white images. Yeah.
And then someone asked about sample prep. How much work is it to prepare samples?
It's not quite as much as it can vary. It can totally vary. But one of the more important things is the sample has to be under vacuum, and it has to be conductive. So the electron beam that's hitting the sample, those electrons need somewhere to go. And so if you don't have a nice conductive path to ground, they just will congregate and give you strange artifacts in your images. So we usually coat our samples. Everything I've shown you today, except for the penny, is coated with maybe 5 to 10 nanometers of either platinum or gold palladium, so that those electrons will have somewhere to go, but the thickness of the coating won't obscure the sample that I'm looking at. And all of those types of sample prep equipment is part of our lab, and is something that you would be able to use and get trained on in as part of the RET program.
We have a couple more questions.
Sure.
Do we identify the color based on wavelengths they emit?
The color of the butterfly wing?
Not sure. I'll see if they want to chime in. Yes.
Yeah, so the way those morpho butterfly wings work is that, yeah, I believe blue is like 450 nanometers. So the way that structure is, like how close those structures are to each other, allow the 450 nanometer wavelength out to give that blue appearance.
And if I might add something, it's Natalie Stingelina. I will be up later. It's reflection, not emission.
Oh, okay, reflection. Well,
So
thank you.
it's like a mirror, essentially.
Okay, thank you.
Looks like there's one more question.
Sure.
So can you tell what the fossils contain, elements, compounds, in the same way that the metals can? Example, can you tell if the microfossils contain different materials that may indicate a meteor hit or volcanic activity?
Yes, you absolutely can. There are limits of only a few, maybe like 4 or 5 elements that we really aren't able to see, but we would be able to see that these are made of mostly silicon dioxide. And then if there was anything beyond that, any other elements, any trace metals or anything like that, it would show up as an additional element on our results. So we would be able to know what to expect. And then if we saw anything differing from that, we would be able to investigate where that came from.
And in regards to blue wavelengths reflected from the butterfly wings, does it scatter the remaining wavelengths from white light?
I'm going to have to ask someone else to chime in.
Yes, I can. I was just going to write in the chat. This depends. What is key in these butterfly structures is that they are what we call hierarchical structures. So you have structures in structures. So you have like these gratings that we have seen, and then when you zoom in, you have other structures in there. So if you have ordered structures, in ordered structures, there will not be scattering. There's always only will be diffraction and reflection, like in a mirror. In case though you place something disordered in the larger ordered structures, then you have scattering. So it depends in case you do it artificially, and it's actually my field. It depends what you want. So if you want to have scattering, let's say if you want to get light into a solar cells, you want to have disorder in order so you can harvest a lot of light and it scatters in all directions into the solar cell or outside an LED. So we can design that. So it's actually pretty, I like it.
Mm-hmm. Yeah, thank you, Natalie. My background is in chemistry, so it's good. I think that's kind of one of the benefits of a program like this, is having all these different experiences and disciplines come together and kind of, you know, I know that a lot of us learn science in silos, in, you know, biology versus chemistry versus physics, but they really interrelate so much that it's definitely something you can explore as part of this program. So our program is pretty flexible with your discipline and whichever kind of area you'd like to go with. But our closely related faculty do a lot with materials, thermoelectric materials and quantum materials. And then there's a lot of environmental remediation materials that they're working on to you know, clean up oil spills and things like that. And that is really, obviously really important to the planet, but it's really the scanning electron microscope and the other instruments that we have in the lab are just essential to really understand what's going on with things like that. So you can really learn a lot. These instruments might take a couple hours to learn initially, and then some practice, and then you'll be able to, like, you know, go on your own and try your own samples and see what you can see.
I think there was one last question. Can you tell if your sample contains radioactivity?
So no, these will not characterize radioactivity. Great. Those are all really good questions. Thank you.
All right, thanks, Elizabeth. So as Elizabeth mentioned, our projects at Northwestern, the Shine and Nuance facilities, can be, we're kind of keeping things very flexible towards the teachers who end up accepting and being part of our program. So if you have a focus in chemistry, we'll try to line you up with a chemistry mentor and things to work with you to create something that is applicable to your field curriculum. We have lots of instruments. We are showing you the scanning electron microscopes now. We like those because we've set them up now to be completely remote. So should things switch or change during the summer, you could still be able to work on all those microscopes as well.
It's also something like during that week when the mentor comes to visit your classroom, it's something that they could do remotely live like I'm doing now for your students. So, but we also have a clean room. We've got other types of characterization materials. We've got X-ray diffraction facilities and all sorts of different things that you could be involved in. Sorry.
Great, thank you, Katie and Elizabeth.
Yes, thank you.
We're gonna, they just let teachers in the Northwestern area know some of the ideas for projects that you could expect to be working on this summer. Now I'm gonna invite Natalie and she is from Georgia Tech, and she is one of the faculty members who will be hosting a teacher this summer to give you a brief idea of the type of project you can be working on at Georgia Tech. And then I apologize for the people from the other sites, just hop on after Natalie in case I have missed adding you into the group, but go ahead, Natalie, thank you.
Well, thanks for giving me the opportunity. I'm really excited about this program. I wanted to participate last year, but obviously things changed all around us. So just a brief background of myself. So you hear from my accent, I'm obviously not from the South. I'm from Switzerland, and I grew up in the Swiss mountains. So quite a change. I did the PhD in Zurich, but then went to England for a postdoc to Cambridge, University of Cambridge, went to industry for a bit, Philips Research, where we did look at, for instance, optics and some of the structures that were just shown before. So it was the main research lab of Philips, designing new types of displays, TVs, etc., lighting, actually large-scale lighting. But then I decided I go back to academia simply to have more scientific freedom. And I went through the ranks at two London-based universities, so back in the UK. And then 2016, I decided I was already like a few years full professors to move, get new challenges. And that's how I ended up in Atlanta. I'm a trained material scientist, predominantly specialized on plastics. But we want to do useful plastics. So one goal of my research is indeed plastics for photonics. So exactly what we have seen here. How can we mimic these butterfly wings? It can be done with very tedious nanotechnology techniques, but then you're limited to very tiny areas. So we really want to mass produce them, let's say for light control in greenhouses, actually generally building a resilient building environment. So you can imagine you can have like the butterfly now reflected blue light back. We want to push that to the infrared. So you have something that is plastic, transparent in the visible, but it reflects the heat, the infrared. So that's the wavelengths above 1,000 nanometers. And therefore then guide the heat away and hopefully use it actually in solar cells. And that brings me to the topics that, for instance, teacher in my lab could do. For a lot of the solar cells, there are now alternatives. You possibly see the silicon solar cells on roofs, whatever. We try to do plastic solar cells, One reason is because they're plastic, they're mechanically usually more robust, but most importantly, they are actually semi-transparent. So you can put them onto windows. You most of the time still have a slight coloration, but you can use that. So we sometimes work with designers or architects. We just put a big grant together with NC State. So that architect can use them in roofs, so they're still semi-transparent. Light comes in, certain light waves, but the others are used to provide some electricity. Again, also very important in greenhouses because the plants only need red and green, I think. So you can harvest the blue light to provide energy. The project that I suggested to Quinn, clearly there's always room, we are flexible, was really looking at those building blocks that we use in these plastic solar cells. So we call them conjugated polymers. So for those with chemistry background, so we have not only carbon-carbon bonds, but it's carbon single bond, double bonds. And therefore you have extra electrons making the plastic actually conducting. And we need that one that conducts electrons, one holes. And projects I suggested was really to study the fundamental. You can imagine, I'm not sure how the molecules arrange is really important. Plastics are like spaghetti. I grew up close to the Italian border. So are they ordered like in a uncooked spaghetti pack? So fully elongated and stretched, that's very good for charge transport. Or are they like uncooked spaghettis after you cook them? Unfortunately, that's usually the case. So you have to figure out how we process them to get a desired, what we say, microstructure. How are those chains ordered or not ordered? Actually similar like with the photonics structures you just have seen. We always have to manipulate order, disorder, and therefore how good electrons or holes, positive charges move, how much they interact with light, etc. So from experimental, I'm not sure if I should stop and have questions. Experimentally, it's usually pretty trivial. I always say my lab is actually pretty boring. It's like a kitchen. You have a hot press, you have things to coat. Of course, then you have the microscope. One of the key instruments is setup, which we call differential scanning calorimetry, where we learn about melting temperatures and out of phase transitions. Because based on that, you can imagine if you have large crystals, small crystals, you will have large melting points, small melting points, etc. So you get indirect evidence of your structure. And I think with that, I see if there are questions.
I didn't see anything pop up, but I hope everyone, I think that was really great explanation of the types of, oh, this is more general. We can get to that maybe later. The question was, how is nanotechnology techniques applied to astronomy? But in relation to the project that Natalie just presented, if there's any questions, and if not, Jim or Therese, do you want to introduce or let, yes, Jim, I see you shaking your head.
Sure, I can go first, Therese, if you don't mind. I can give you a little idea of what we've done in the past and then a little preview of what we expect to do. We haven't finalized projects quite yet. But in the past, for those who are interested in electronics, we've had RETs work with a group that's working on spintronics. Those of you who teach physics recall that the electron, in addition to the charge, which we exploit in electronics, has a spin, an intrinsic spin that can also be exploited to make different types of circuits. And these are being talked about as a way to realize quantum computing. So that's a project where they've been involved with before. Thin film deposition using molecular beam epitaxy, a real advanced lab method for making thin film sensors, has been a subject of past RET projects. I mentioned the ultrasonic probe, and then an environmental bio project, which resulted in the paper that's in the chat box, was the effect of silver nanoparticles on aquatic organisms. As you know, silver is antimicrobial. Making it into nanoparticles makes it very antimicrobial, and it gets introduced into various consumer products. It then goes down the drain, passes through the sewage treatment plant, and enters the environment and the rivers, where it can have real antibiotic effects, undesirable ones. So that was a past project. This year, we're looking at groups, the faculty members that have expressed interest are working with organic electronics. In other words, making electronics not out of silicon processes, but out of organic molecules, which allows you to roll coat these things like Scotch tape, which would be very exciting. Mechanical engineers are working on MEMS-based devices, micro-electrical mechanical systems that are like those very, very small mechanical systems engineered in silicon. So that's a research topic. A couple of folks are working in the chemistry and biochemistry area as well. So there'll be a range of topics, and I think that they'll be appealing to people teaching physics, physical science, chemistry, biological sciences, as well as even technical education. Therese?
Yeah, I'd like to just introduce Professor Steve Descharmes, and he'll give you more information about the projects that we're going to have. And then I'll put in the chat the link to our website, which has a couple of the projects up there, but he'll go over everything, I believe, correct? So Dr. Descharmes, do you want to take over?
Okay, thank you. I'm going to share my screen here. I have to say I'm not as well prepared as I should have been as to what projects to talk about. What I do want to answer here is the types of projects you'd work on. And there have been some questions about what's it like working in a research group at the university. And this what I'm saying, of course, applies to all of our institutions. We're typically involved in various kinds of materials and nanoscience. That's the center theme of the larger projects. And the RET program is an integral part of this. So I took a picture of a typical research group. It happens to be mine in the lower right here. And the reason I did that is because, number one, there's going to be a wide variety of environments. The research groups have personalities just like individuals do. Sorry about that. I'm pressing the wrong buttons here. Okay, so, and you'll typically have people in this research group ranging from a professor, some collaborating professors, some visitors. In my research group, depending upon the year, the age range can span 70 years when I have some of my senior colleagues join us, all the way down to high school students. And one of the themes I want to tell you here is this is multi-tiered mentoring. Everyone in here is learning from each other something important. If it's a high school student, like Cole here, or a high school teacher like Steve, he's quite senior by this time in our group. He's been around a lot. Melissa Terry, who's a newer high school teacher. REU students from other universities, graduate students and undergraduates from my group, visiting scientists from China. We're all learning from each other. I'm learning about mentoring high school students from our teachers. I'm learning about working with a variety of students from our visitors. And it was asked early on, I think it was Dylan asked, what about training? Well, everyone here gets trained. In fact, when they join my group, they have to be trained on certain specific things that we do all the time. We also are working with organic electronics. And that's why, for instance, I have a lot of chemists. The two high school teachers actually have chemistry training by profession. And even some of my graduate students had chemistry undergrads. So the multidisciplinary aspect is very important. We work heavily with engineers because organic electronics implies you're making device with that. And that's typical of material science. And so our research is always a team effort. It's ongoing research. If you're there only for a summer, you're seeing a snippet of what's going on, but you're seeing the full effort working together. We tend to be multidisciplinary. As I mentioned, we provide training. All these wonderful facilities that our universities have for electron microscopy, scanning probe microscopy, X-ray diffraction, nano fabrication, clean rooms, and so forth. Those are all common themes to our institutions. and they all have their own infrastructure and training. For example, I personally never received training in X-ray diffraction or scanning probe microscopy or nanotechnology or nanomanufacturing. I actually teach those to my visitors, including the high school teachers. They learn that by going to the center and being trained there on the instruments that are state-of-the-art research instruments. These are not toy instruments. These are not tools intended only for teaching. They're tools intended for research. And that's what we do in the laboratory. So the types of things you'll do day to day will depend upon the work. It might be synthesizing a compound. You might be growing crystals. You might be going down to the electron microscope to look at structure, X-ray diffraction to look at structure. You might be going to the scanning probe microscope. And if you're the teacher for the summer, it might be that you'll get specific training on the scanning probe instrument or the electron microscope. There's not usually time to do many of those. And you'll work in combination with a graduate student or undergraduate student who's our group expert on that. And so if you weren't trained on the electron microscope, you might go down with the student working on that, like Shashi here, and you'll get your samples measured, but you'll be there working with him. So that's another feature of this multidisciplinary, multi-tiered level. Our research efforts in Nebraska range from biomimetic materials to organic, electronic, and mechanical materials. We have a lot of magnetism and nanomagnetism work also going on. It's a combination of material science and materials engineering. And I like to say that nanotechnology is really just the tip of the iceberg. All the science and engineering underneath is what we do every day in the laboratory. I'm welcome any questions you might have.
One question popped up. Jim, is there a link to RET project descriptions for Minnesota?
In progress.
Okay. We will make sure that will be added to the RET site link that I shared at the beginning that I'm going to post again in the comments at the end of this. Are there any questions for Steve? That's great. All right. Well, thank you, everyone, for joining and giving that overview. Excellent. And there are 5 projects or 5 slots at each of the sites for this summer. I just want to go back to the question about virtual. We are proceeding and planning, fingers crossed, that the research will be face-to-face. As you know, since we're networking across 4 sites, much of the other activities will be virtual because of that, but we are really hoping to be face-to-face. I can tell you that at Georgia Tech, I was really happy to see that in Georgia, at least, K-12 educators and staff have been pushed forward in the vaccine, right? You guys are going to start being able to get your vaccinations on March 8th. So, and then universities at Georgia, again, are going to be a part of 1B. So the faculty and staff and student workers that you'll be working with will also hopefully be vaccinated by June. So we are hoping, working, planning to be face-to-face, but as you know right now, things are uncertain, but that is what we are certainly hoping for. And if other sites at other states, if you have anything to add as far as, you know, the vaccination, since it's state by state, if you want to share anything else about hoping to be face-to-face for the summer.
Well, in Nebraska, we're planning face-to-face. And so, yeah, we've got the same scenario, you know, that the vaccines are coming and people are having the opportunity to take them. And so we feel by June that it's a pretty good possibility that we can have the labs open and, you know, the program will continue as we planned. But we'll keep everybody up to date.
Yeah, we're currently working in the lab socially distanced. That's been the case since last summer.
That's true also at Georgia Tech, that the faculty and the graduate students and everyone are in the labs right now.
Yes, same with Northwestern. People are in the labs and have been working for a while with the COVID measures in place. So we are also anticipating on having it in person.
With that, if there's any other questions, and I'll keep monitoring the chat, we're going to get to our final activity for this morning. Thank you all for spending your time with us, and that is the STEAM Kit raffles. So we sweeten the deal, hoping that you would spend some time with us this morning. And I'm going to turn that over to Leslie to handle our raffle. So.
Okay, good afternoon. So in these STEAM kits, you are going to find, we're going to have 4 lesson kits that are going to be put together. Each kit will come in a plastic shoebox, and it'll have enough materials for several students to go ahead and do. So if they have extra time after they've finished an assignment, they can go ahead and do one of these kits. It'll also have a page of instructions, which will be laminated, so they could last a long time. And in those kits, we have exploring hydrophobic properties. That will include magic sand. And then we also have exploring materials, which is thin films, which will have a pan, it's a cake pan with a good supply of Tyvek and nail polish, and in the instructions. Then we have exploring size and scale, which is a card activity where the students go ahead and line up the cards from nanoscale to macro scale. And that's really a challenge at all times. No one has ever gotten all the cards right. So that will that'll be a lot of fun. And then our last activity is exploring forces at the macro and nano scale, which includes little tiny doll cups and clay. And then we also surveyed some teachers that we've worked with to sweeten this pot of the STEAM kit for classroom supplies. And we basically got what I have listed here: Post-its, pens, pencils, binder clips. Push pins seem to be a big thing, thumb drive, and then a diffuser. So this is a lavender diffuser to make your classroom smell nice. So I'm going to go ahead with, I've been looking at the attendance, and I will draw 5 names. So the first name we have is Eva Nelson. Second name is Danielle Malcolm. Third name is Mike O'Rear. 2, 3, 4. Then we have Karen Shee. And last, Mary Kathura. So if you all, I will reach out to you via email so that you can go ahead and I can get your mailing address, and I will probably be shipping these in about a week or so. And if you have any questions, you do have my email from reaching out to you all. You can contact me as well. Thank you.
Thank you, Leslie. I was teasing her that I wanted her to dress up a little bit like Vanna White, but that was an excellent presentation of the raffle. And with that, we are finishing up. I just put the relevant links in the chat again. In addition to people who won, we will follow up with an email this week to everyone who registered with all of the links that we mentioned today, the link to the application, to link to the RET sites. This presentation, which is being recorded, as well as the PowerPoint presentations you saw today, will also be up on that RET site sometime this week. And if there are no more questions from anyone, thank you again very much for spending a few hours with us your Saturday morning. We really appreciate it. And I'm hoping that you'll apply and I'll get to know some of these teachers in the Atlanta area this summer as you work on your RET.
Thank you.
All right. Thank you, everyone.
Thank you. Thanks, Quinn.
Thank you. Bye from Minnesota.
Thank you.
Bye, everyone.
Bye, everybody.